Welcome back, my best chem students, or my beloved chem students. You're really moving forward very well. We're now just at our last 3 free response questions. So let's take a look at question 1. Again, AP, and rightly so, is very intent on you being able to integrate knowledge, not just plug and chug into equations. So let's take a look at what we have here and underline or list or do something to your key points here. So this is a gaseous reaction. We're dealing with a decomposition that is heated. Now, the people who wrote the question didn't need to tell you this. It was very nice of them to tell you it was endothermic, but really should have been able to get that from the other context there. Now, we have 3.509 grams, and that's our initial SO2Cl2. We have a volume of 1 liter, and the temperature is 375. Now, what I think is helpful is for you to label these. So we have a mass, we have a volume, and we have a temperature. I think if you label them with the symbols that we would use, that can help give you direction to formulas that are needed. So since it is endothermic, another way of writing that is to say that our enthalpy delta H is positive. Now, the first question says, what is the pressure of SO2Cl2? And we're doing it initially because it says before there's any dissociation. Now, I see a mass, I see a volume, a temperature, and a pressure, and my mind's going to go to Pevnert. Now, there's 2 ways you can do this. Mass to moles, use molar mass, and you could, if you wanted, do this in 2 steps, and if you calculated the moles, you get 0.0260, probably 0 moles. We want to go to 4 sig figs here. Now, my mind sees that mass, and instead, my mind likes this one. Now, do you think I care which one you use? Absolutely not. But I think it's helpful to know that you can always pop in mass over molar mass for your moles when you see that. So I'm going to solve this for pressure. My mass is 3.509. The molar mass of SO2Cl2, you should be able to calculate without my help at this stage. So that's the molar mass. Now, we're going to be dealing, when you're working on equilibrium, you really want to be working with atmospheres. So I'm going to use 0.0821 here. And it does say in atmospheres, by the way. And then my temperature has to be in Kelvin, and the writer of this question was very nice to give me the temperature in Kelvin. And I have to divide by my volume, which fortunately is a nice, simple 1 liter. Now, if you crank through that algebra, you should get 0.800 atmospheres. I took that to 3 sig figs, because my volume's in 3 sig figs and my temperature's in 3 sig figs. Okay, so that's part A. No equilibrium yet. That's going back to tools of the trade, and I hope you've really seen why I had to start with kind of an awkward place in our notes. Now we're going to let the system come to equilibrium. I want to use rice. You don't have to, but I'm telling you, 9 times out of 10, if students don't use rice, they're going to get lost. Rice gives a good framework for problem solving. Now, these are all gases. I hope you know that. I'm not going to bother writing it down because it's right up here, that they're all gases. Now, part A told us that this was 0.800 atmospheres. We had none of this initially and none of this initially. Now, you may be asking yourself, oh my gosh, what am I going to do if I couldn't get A? Because my B depends upon that answer. Just assume something. If you don't know A, write something simple. I mean, I would have assumed 1 atmosphere. assume 1 atmosphere for your partial pressure of your SO2Cl2 initial. But state that assumption. All right. Now, I have the correct 0.800, so I'm not going to put in a wrong answer there or I would lose points. You've already lost your points on A. If you state your assumption clearly, you can still get some good points in B. Now, this has no choice but to form product, so I have to consume reactant, and since these are all a 1:1:1 mole ratio, that's minus X, and plus X. Now, E, remember, is simply equal to I plus C. So let me see if I can get a better color here. E is going to be 0.8 minus X. This is X, and this is X. So now I've developed a framework from which to really think through the problem. Now, in here, it tells me I'm still at the same temperature, so that's good. I'm at equilibrium. Now, what that means, if I am at equilibrium, is that, sorry, it just doesn't want to grab for me. Come on. All right. I want to be focused on my equilibrium values up here. All right. Now, it tells me, the problem says that the total pressure is found to be this. Well, this requires you to remember Dalton's law. Dalton's law tells me that my total pressure is equal to my sum of my individual pressures. And these are all partial pressures here. So that means my partial pressure, it's 0.8 minus X, plus my partial pressure of SO2, which is X, plus my partial pressure of Cl2, which is X. Dalton tells me that that's going to be 1.43. So if we do just a little bit of canceling here, minus X plus X, now all I have to do is solve for X, and you'll find that X is equal to 0.630 atmospheres. Okay, now that means that's equal to my partial pressure of SO2 because S represented my SO2 partial pressure. That's also equal to my partial pressure of Cl2, again, because X represented that equilibrium partial pressure. Now, my partial pressure of SO2Cl2 is equal to 0.80 minus X, which was 0.630. So that one is going to equal 0.170 atmospheres. Okay, so now I have all of those equilibrium pressures. And so that's part B. Now let's go on to part C. Part C says, given the expression, and we're given the luxury of choosing whether we want to do KP or KC. And we need to set it up and calculate the value, both an expression without numbers and the value. You can do this in moles and deal with KC, but you're going to backtrack and do a whole bunch of extra work. If that's the way your mind wants to do this, you are welcome to do that. But I already have all of my equilibrium partial pressures. I would rather set up KP, and then all I have to do is substitute those values in. Now remember, it's always products on top. You cannot use brackets if you're dealing with partial pressures. So once you've made that decision to give it in terms of KP, you are bound to using the capital P's and subscripted. If you use brackets, you would lose points. So that's the expression. Captured a point there. Now it says to give the value. Well, we just did that in part B. We calculated those values. Again, you can assume some reasonable values, but if you didn't get those partial pressures, you might want to go back and start all the way back and convert this to moles, then divide it by volume and deal with Kc if you're struggling. I'm going to go ahead and plug in our values from our previous problem. 0.630 times 0.630 divided by 0.170. And when you do this algebra, you should get 2.30. And we don't really worry about units for Ks. Now, if you're IB, they like to deal with that. So we have atmospheres times atmospheres divided by atmospheres. So technically the unit is atmospheres. AP isn't too worried about that, but IB will get into that. So just an FYI. Now, D says I'm going to raise the temperature. So in other words, I'm going to stress the equilibrium, or I'm just going to adjust to see, will an increase in temperature give me more products to make lots and lots of money? So I've got SO2Cl2, and I've got SO2 plus Cl2. Whoops, sorry about that. Now, I'm adding heat on the reactant side. The reason I'm adding heat on the reactant side is because the problem says it's endothermic. Endothermic means heat is entering the reaction. Now, you can actually use your little pencil trick to make sure you get the right answer. So there's equilibrium. I'm increasing my reactant. I'm adding heat, and heat's a reactant here. Now the question is, which way is it going to shift? Well, it's going to shift to make more product and consume reactant. All right, so your answer is you always want to write this qualifier with temperature. Since the reaction is endothermic, that's what you need to start with. That makes it clear to the person with whom you are justifying your claim is that you understand the difference. So since it's endothermic, I'm going to shift to consume reactant, right? It's all about what's happening to reestablish equilibrium, consume reactant, and what I'll do then is form product. So my product partial pressures would increase. My reactant partial pressure would decrease. Now, in this case, I'm going to make a new K. All right. Now, my K at 500, since I have more product and product is in the numerator, my K at 500 would be greater than my K at 375. So when it's a LeChatelier and you are changing temperatures, you end up establishing not the same, we're not reestablishing the same equilibrium, we're going back to a new equilibrium. Okay, so that would be your justification. Now I'm going to do 2 more AP questions just to help you work through these. So until then, this is your best chem teacher.